I'm going to talk about dropout, in particular the role of dropout as an explicit regularizer in machine learning problems. And this is based on a series of work with my PhD student, Purya Mianji, who's in the audience, Nati Cerebro at TTI Chicago, Rene Vidal at Hopkins, and Peter Bartlett at Berkeley. Okay, so it must be amply clear by now that one of the most pressing challenges in deep learning is to understand generalization. In other words, why is it that the overparameterized neural networks trained with seemingly not enough training data generalize as well as they do? And learning theory suggests that there must be an inductive bias or a useful prior that helps with generalization. And the goal is to understand the nature of such an inductive bias, and understanding the nature of such an inductive bias could hold key to not only explain but potentially improve the practice of deep learning. Now, classically in machine learning, we incorporate such an inductive bias either through restriction of the hypothesis class, selection of a hypothesis class, or by explicitly enforcing a regularizer in the objective. Right? But the practice of deep learning, modern machine learning, is quite different. Right? There's no explicit regularizer in the objective, and there's seemingly no restriction on the hypothesis class that we're working with. Right? So where is the inductive bias coming from? Right? One potential source is the choice of the optimization algorithm itself, often a variant of gradient descent. Here, the inductive bias could be implicit in the geometry of the local search. Another potential source is explicit algorithmic regularization techniques, often proposed as heuristics, such as weight decay, early stopping, and dropout. And in this talk, I'll focus on such a role of dropout, and I'll illustrate dropout with some explicit forms of regularizers in various machine learning problems, and discuss how they enable capacity control. Okay, so what is dropout? So dropout is an algorithmic regularization technique proposed not so long ago, or eons ago, and from Srivastava et al. From Jeff Hinton's group. And it's basically the following procedure. Right? So at the time of training, during the forward pass, we randomly drop, or turn off, if you will, a random subset of neurons for when predicting a label on a given input data. And it works actually remarkably well. It's a fairly simple algorithmic heuristic. It works remarkably well. In fact, I was running experiments a few years ago on large vocabulary continuous speech recognition, and we noticed that using dropout, the acoustic models that we trained were remarkably better than those trained without using dropout. And we wanted to say something in the paper as a way of explaining why that might be the case. And all we could find when referred to the original paper was that dropout was a way to break code adaptation and balancing networks. And we couldn't quite understand formally what that meant, or why dropout would behave in that way. And even if it did, why that would help with generalization. Right? So one of the takeaways, I hope, from this talk would be to at least get a formal sense of what these might mean and why it's useful for generalization. Okay, so here's an outline of the talk. So I'm going to start with problems that we understand well, matrix learning problems, in particular matrix sensing and matrix completion, and discuss the role of dropout there. Again, I'll show explicit regularizer that show up, and they're data dependent, and I'll discuss why they enable capacity control. I'll then switch gears and talk about regression using deep neural networks, make some connections with path norm and Persian max regularization. I'll show some empirical results which verify the theoretical guarantees that I will provide, and then we'll discuss what's next. Okay, so let's start with matrix sensing. So matrix sensing is the following problem. We're given where the goal is to recover an unknown matrix, M star, with some rank R star, given linear observations, which are basically linear products with M star, and a bunch of sensing matrices AI. Right? And we assume that the number of measurements that we have is much smaller than the size of the matrix. And as well as the rank is smaller than the dimensions of the matrix. Okay. A natural learning rule here is empirical risk minimization, right? Except we choose to represent our matrix variable M in a factored form. So we represent M as UV transpose, right? And would seek a minimizer of this empirical risk. The algorithm, the optimization algorithm that we choose to find the ERM is stochastic gradient descent with dropout. So what that means is that for each component function here in the finite sum, right, so basically for each input ai and the corresponding label yi, I draw an IID diagonal random variable b whose diagonal entries are 0 with probability p, which I'll refer to as dropout rate, and 1 over 1 minus p with probability 1 minus p. Right? So for each sample, we randomly drop certain factors in certain columns in U and V, and scale up the remaining to make up to compensate for the pruning. Right? So that's dropout for matrix sensing. And what we look at, and this is a simple exercise. So this is what I'll refer to as dropout objective. This is what we wanted to minimize originally. This was our learning rule. Right? We chose this algorithm. So what we are actually minimizing is dropout objective, and it's a simple exercise. If I just take expectation here with respect to these Bernoulli random variables, to see that the dropout objective that I'm minimizing actually is the original objective plus another term. Right? And we'll refer to this additional term as an explicit regularizer due to dropout. Right? And it depends on the dropout rate. And the regularizer itself that's manifested is data dependent, in fact, very sample dependent. Right? And we'll actually simply look at its expected value. Right? So rather than focus on the sample specific instance of explicit regularizer, we'll look at the expected regularizer of expectation with respect to the data, the sensing matrices AI. And more importantly, because we are looking at a minimization problem, right, it suffices to just look at the minimal regularizer value over all factors of a given matrix M. Right? So we refer to this as induced regularizer. Right? This is at optimum. This is the regularizer value that the factors will take. Right? And so we'll refer to this as induced regularizer. So what we really want to understand is what is the nature of this induced regularizer. Clear? Okay. So here is a first surprising result that we thought at the time was quite surprising. So if I assume that the sensing matrices are Gaussian matrices, so each entry is sampled IID from standard normal distribution, mean 0, variance 1, then the induced regularizer is nuclear norm. Actually nuclear norm squared, but behaves as nuclear norm. So induces low rank solutions. Okay? And this is fairly easy to see. So I'm just going to run through a quick proof and illustrate something and show that something interesting will emerge that will be nice to see. Okay, so this is just from definition. So the expected regularizer is just, I'm pushing the expectation in here. So this is what the empirical regularizer was, right? So this is expected regularizer. And again, basic manipulations show that this expected regularizer is sum over the factors of the products of the norm squared of the factors. And to some, this may already start looking familiar. If you think of this as a single hidden layer linear network, this is, I will come back to this, but it looks like path norm. Right? Now, this is just using Cauchy-Schwarz inequality, lower bounded by this quantity, which is sum of product of the norms, and using the fact that these are rank 1 matrices. So nuclear norm is equal to the spectral norm and equal to the product of the norms. Each summand here is equal to the summand, so that's equality. And then using the triangular inequality, this is lower bounded by the nuclear norm of the sum of these factors, which is again nuclear norm of the matrix. Right? So the regularizer, explicit regularizer here is lower bounded by the nuclear norm of the matrix squared. So is it actually achieved, or when is this achieved? Is this the induced regularizer as I claim? Right? So it's easy to see that this lower bound is achieved for all factors U and V, for which the product of the norms is all equal for all factors and equal to the nuclear norm of the matrix UV transpose. Right? And that's easy to see because if you just plug this in here, right, you get this, right? So this bound is trivially achieved. We'll refer to these factors as balanced, right, or equalized. This is what we refer to them in the original paper. And a key result here is that, in fact, we can equalize any pair of factors, right? So for any uv, there exists a rotation such that when I rotate these factors u and v with the same rotation matrix, they are balanced, right? Hence, the induced regularizer due to dropout in matrix sensing is nuclear norm squared, right? So the reason I went through this derivation is that this is interesting in the sense that dropout actually favors solutions which are balanced, right? This is what perhaps original authors would have meant by dropout balances networks. And it's the right kind of inductive bias, at least for this, this learning problem for matrix sensing, the nuclear norm, right? And again, what's happening here is it's spreading this budget, if you will, of nuclear norm across all factors equally. Right? That's the inductive bias here. We can go through a similar calculation for a special case of matrix sensing, that of matrix completion. So for sensing matrices that are indicator matrices, so AJs or EI EK transpose, where the row, so it's all zero matrix, but except at the entry IK, right? Where the rows are sampled through some distribution on rows P, the columns are sampled through some distribution Q. And what we get here, again, doing similar calculations, is the induced regularizer due to dropout is weighted trace norm. And this, again, has been studied over a decade ago and was shown to yield state-of-the-art results in matrix completion. And Nati will actually tell you a nice story how this came about through a bug in the code. Right? And again, we can leverage the previous results to give generalization bounds. I'm not going to dwell too much on the bounds here. I just want to illustrate the role of dropout as explicit regularizer. Okay, so here are some test experiments on matrix completion. How does it actually do? Right? So here's some plots. So I'm working with movie lens data sets, one of the largest data sets I could find for matrix completion. There are 10 million ratings for 11,000 movies from 72,000 users. And what I'm showing here is train MLC, test MLC as a function of number of iterations of the algorithm. Right? So for dropout, for various different values, along also with plain SGD with no dropout, the train RMSE decreases fairly quickly. Right? And the test error is also decreasing. For dropout, different variants, it's keep decreasing. For SGD, it's interesting, at some point the train error starts increasing. So even though SGD has been shown to have implicit inductive bias, which is also related to nuclear norm, we were very surprised by this. Here I show generalization gaps, basically showing that the generalization gap between, so the difference between train MSC and test MSC doesn't increase too much if we have sufficient regularization. For SGD, it's not really controlling. This complex image is not really explaining the generalization gap. We also looked at the same set of experiments with different over-parametrization sizes, so different D1s. And here again, we saw that for even in over-parameterized regime, right, across different regimes, dropout always did the best. Right? And SGD actually, this performance starts getting worse along as I increase the size of the over-parameterization. In fact, even if I cheat, if I actually pick the iterate of SGD, which does the best on the test set, even then it's not as good as dropout. And this is a very large data set, so this is significant. Okay. So now let me switch to deep neural networks. So this is the setup I'm looking at, regression with deep neural networks. It's a standard setup. So my input space is X, some D0 dimensional feature space. My output space is Y, some decayed dimensional label space. There's an unknown distribution on X cross Y. I'm looking at the hypothesis class of feed-forward neural networks with K layers. Right? So these parameters here are WI's different, weight matrices at different layers. These are DI cross DI minus 1. And I'm doing regression. I'm looking at squared L2 loss. So the loss between the label instance Y and Y prime is the square of the L2 norm of the difference of the vector. Right? And goal here again is to find a hypothesis in the hypothesis class with a small population risk. The learning algorithm that I choose, given n samples drawn IID from the distribution, is again empirical risk minimization. Right? How I find this ERM is again through dropout, using SGD with dropout, and which is basically minimizing this empirical objective. And for now, I'm just considering dropout in the final hidden layer. Right? So I can write the objective here again as before in the following form, where the matrix B or IID diagonal random variables with Bernoulli entries. Okay. I'll refer to two quantities, so just to set up some notation here. So the outgoing weight vector from the jth hidden node in the last layer, I'll refer to as WKJ, and the activations at that node I'm going to refer to as AJ on a given data point X. So the first result is again cranking through this machinery. The expected regularizer due to dropout on this problem is basically sum over the hidden nodes in the dropout layer of product of the norms of the outgoing weight vectors and the second moment of the activations. And this is again interesting, as I had mentioned earlier in the case of matrix sensing, because there are close connections here with path regularizer, L2 path regularizer. So in fact, if I look at the special case of two-layer ReLU NN, neural network with ReLU activations, and further assume for simplicity that the distribution is symmetric and isotropic, then this regularizer reduces to exactly what is known as L2 path regularizer. Okay? What this regularizer in the general case is essentially a data dependent version of L2 path regularizer, I would argue, right? And the goal here is to understand what kind of capacity control does this explicit regularizer provide in this setting. Okay, so for now, for simplicity, again, I'm going to assume that the output dimension, so it's a single. So I'm just predicting a scalar label, right? So dk is equals to 1. I'm going to consider the following size bounded hypothesis class, F alpha, where this is all k-layered neural networks with the value of the regularizer, explicit regularizer that we just showed, bounded by alpha. Right? And one result which was quite interesting to us is that we can directly bound the expected Rademacher complexity of this hypothesis class in terms of this alpha. Right? So the Rademacher complexity of this hypothesis class is exactly bounded by square root of dk minus 1 alpha over n, where dk minus 1 is the width of the last hidden layer, the dropout layer. It's not the width of the network. The network itself could be very wide. So it depends mildly on the width, if you will. And there's clearly no explicit dependence on the depth or even the width. Right? If dk minus 1 is much smaller, the last hidden layer is much smaller, which is often the case in practice, then it's really width independent. Right? And the key observation here is really when we try to bound the Rademacher complexity for any class of neural networks, right, we can bound it in terms of the L1 norm of the vector, whose entries are essentially the products of the outgoing weight and the activation at that node. Right? Sum over again the hidden layer of the absolute values of the product of the outgoing weight and the activations. Okay? And this can trivially be bounded by using Cauchy-Schwarz inequality, using what we have here, the expected regularizer for the dropout. Right? So this is exactly the expected regularizer for dropout. This is how we get this bound. Okay? So what we're basically showing is dropout controls the Rademacher complexity directly in deep regression when we do dropout on the last hidden layer. Right? Another interesting thing to look at or think about is when is this? So dropout is trying to minimize some upper bound on this quantity. Right? When is this inequality tight versus loose? Right? So if the neurons at the hidden layer co-adapt in a sense that a large number of them are 0 at the same time, then this quantity is going to be much smaller, right? So much larger, right? So this inequality is going to be very, very loose, right? Whereas if all of these summands were all equal, right? So all of these summands here were all equal, then this actually holds with equality. Right? So dropout in trying to minimize this upper bound is again trying to equalize networks, and in trying to again minimize this upper bound is trying to break co-adaptation, so they don't adapt in a way that a large subset of them are off for a given instance. Right? So this is, again, what perhaps the inventors of Dropout could have meant by breaking coadaptation. In fact, for linear networks, our previous work showed that Dropout does equalize the networks. So the second inequality actually holds with equality. Okay, so again, if I have this upper bound on the Rademacher complexity, think of this as actually an upper bound on the generalization error, and we can write this formally, but we can also look at what kind of a generalization gap or upper bound on the generalization gap we get with this complexity measure. Okay? So here are some experiments on CIFAR 10. Right? So there's 50,000 training sample, 10K test, and I'm plotting the train error and test error as a function of the width of the last hidden layer, dk minus 1. Right? And again, I'm using plain SGD and dropout with various different dropout rates. Right? So here I see training error decrease very quickly for all of the algorithms as well as the test error. And the generalization gap here, so this is basically the observed generalization gap. And this is what the theoretical bound predicted. Right? And it stays pretty tight for dropout. For SGD, of course, it's not controlling that measure. This bound doesn't tell me anything, even though the SGD solution generalizes pretty well. Okay? We also did a test suggested by an earlier work from Dan Roy, where we constructed a binary classification on MNIST, where we basically discriminating between the digits 0, 1, 2, 3, 4 versus 5, 6, 7, 8, 9. We train a 3-layer deep neural network with dropout on the last hidden layer. It has around 300K parameters, so significantly over parameterized. We see a test error of 0.0084, so 0.84%. And train loss plus dropout complexity, which is the upper bound we're suggesting through our analysis, is 11%. Right? So it passes at least one litmus test. Okay. Let me start winding up. I want to say something about role of parametrization. So it's not just the choice of the algorithm or the algorithmic heuristic. Often how we parameterize our network also plays a role, right? So if I look at the explicit regularizer due to dropout in linear regression, so least squares linear regression. So it's just a single hidden layer, a single layer linear network. Then I see that, again, through the expression I showed, that the induced regularizer is data dependent and actually depends on the empirical second moment matrix. Right? And it's not a very useful regularizer if you think about it. In fact, if C hat is identity, then it provides Tikhonov regularization. Otherwise, the global optimal solution to the least squares problem is simply a scaling of parameters and isn't really doing anything useful, right? So what's happening in here, right? So one suggestion might be that because it's due to the factorization, right? So we represent a linear predictor in deep neural networks in factorized form, so that could have an implicit bias as well, right? But we showed a similar result for deep linear networks, right? So in a previous work, we looked at deep linear networks, and we essentially see the same data-dependent regularizer, which doesn't amount to do much, right? So what's happening? I mean, there's a potential contradiction because we already saw that for matrix sensing, which also has a linear network, it was a richer regularizer rather than just a data-dependent regularizer that does nothing, right? So the answer here is actually matrix sensing can be seen as an instance of a convolutional, single-layer convolutional network. And the convolutional structure is essential in linear networks to give you richer implicit bias here. In deep neural networks, we are already good. Okay, so I have a couple more minutes. So let me conclude with some future directions and then a summary. So on the way, trying to analyze the Rademacher complexity of the function class, a norm-bounded function class due to dropout, we recovered this inequality, which was quite interesting. This holds for all neural networks, for any class of neural networks. And what basically this is suggesting, if we can bound this activation in terms of product of spectral norms, is that if we assume this spectral norm bound on the products of the weight matrices of our network, then we get an upper bound on the Rademacher complexity that's size independent, that's depth independent, that's width independent. Again, there's mild dependence on the width of the last hidden layer, but again, it could be much smaller than the actual width of the network. Okay? And this improves on previous results from Benham and Nati, as well as Peter Bartlett. So they make a similar assumption, spectral norm bound assumption as us. In Neshabur et al., there is a polynomial dependence on the depth as well as dependence on the width. The dependence on the width was taken care of by Bartlett. And more recent work, Golovich actually does give a completely size-independent upper bound on the Rademacher complexity, but they make a much more stringent assumption on the network class being bounded in terms of the product of the Frobenius norms of the weight matrices. Right? So that was quite interesting, and pursuing this further and verifying this, first of all, to make sure it is still a valid measure of complexity, is an interesting future direction. Let me skip this. One thing that does remain and is pretty interesting to us is that we don't have any optimization theoretic guarantees here. In fact, I want to say that the original problem that we wanted to solve was really that of computation. I mean, the open problem really in deep learning is one of computational learning rather than statistical learning. Right? So we don't have any optimization theoretic guarantees here. So does dropout training even find an approximate minimizer? We don't know yet. For linear networks, we did show that strict saddle property holds for dropout objective. So there's perhaps some hope there. Another interesting direction is what happens if I actually did drop out each layer rather than the last hidden layer. Right? Again, here for linear networks, our ICML paper from this year looks at the regularizer that's induced. And it's actually composed of several subregularizers, each of which can be related to nuclear norm, but it's not clear exactly what it is doing. Okay, so let me conclude with a summary. So what basically the point I want to put forth is that dropout is really a very exciting, interesting algorithmic heuristic which yields useful inductive biases for several learning problems. More generally, the message that I want to convey is that understanding how various algorithmic heuristics provide regularization in deep learning can help identify inductive biases that may help more generally with explaining generalization in deep learning. In our instance, it did provide novel insights into the generalization analysis of neural networks. And it also revealed that the network structure, or how we parameterize a network, also plays an important role. It's not just about the algorithmic heuristic. I also want to conclude with a general message. So I said in the beginning that there are two potential sources still of incorporating inductive bias in deep learning. One is rather implicit in the geometry of the optimization algorithm that we use. The other is, again, explicit algorithmic regularization techniques. I do think they provide different, fundamentally, they have a different nature of inductive bias, these two approaches. Which is why we saw the performance of SGD degrade after a while. Another aspect is, of course, we don't really have quite the knobs in implicit regularization that we can fiddle with, just like we do with explicit regularization. But more generally, I feel like the picture that we should have understanding explicit regularization versus implicit regularization is that there are really two different learning algorithms. Right? One is the classical way of thinking about it, where I'm actually designing learning algorithms and optimization algorithms for the learning problem, where I'm trading off the empirical error with a complexity measure. Right? And these bounds that we show will explain the generalization behavior in those for those learning algorithms. And the other is where the learning problem algorithm is posed as finding a minimal norm solution subject to interpolation. Right? And that's fundamentally a different algorithm. Right? Maybe we didn't intend to implement that learning algorithm, but when we drive the training error to 0, right, we're in effect implementing that alternate learning algorithm, where the notion of implicit inductive bias becomes fairly important. Okay, so I'll stop with that and I'll take questions. and here are some references.